Hello everyone, I hope you're doing well today. Today I'm here with a new science video for you guys. In this video, I'm going to be explaining the kinematic equations and doing some practice questions regarding them. So what are the kinematic equations? These are the equations that describe the motion of objects based on their initial conditions. These equations do not consider the various forces impacting the objects and can be used to predict several properties of motion. They utilize the time spent by a moving object, their initial and/or final velocity, their acceleration, and the distance traveled by the object. These equations were formulated by Galileo and Isaac Newton. These equations are very useful in the field of astrophysics, as they're very adept at describing the interactions of celestial bodies. These equations are also very good at describing freefall mechanics and the movement of objects in freefall. So these are the four major kinematic equations. On the left-hand side here, you can see the equations can be used to solve for specific variables, with two of them being used to solve for the distance traveled by an object, and the other two being used to solve for final velocity. However, these equations can be used to solve for any of the terms used in the equations by substituting values in and calculating the missing expressions. For example, if somebody wants to calculate the initial velocity and they have the final velocity, acceleration, and time, they can plug the numbers in and then solve the equation to find out the initial velocity. They can also do this for any other variable. Sometimes these equations are used in conjunction to find multiple missing variables. On the right-hand side are the same equations, just lifted in a different format. The triangle sign you see here is called delta and represents a change in a certain variable. So delta x, as you can see in equations 2 and 3, stands for the change in distance. And delta x in equation 4 also stands for the same thing. VO here, V0 means the initial velocity, and the V shown here means the final velocity. Acceleration and time are shared between both images. So let's start with one practice problem. So an airplane accelerates down a runway at 3.2 meters per second squared acceleration for 32.8 seconds until it finally lifts off the ground. Determine the distance traveled before takeoff. So the best way to start with these problems is by listing what you know and what you don't. We know the acceleration of the plane, we know the time, we know the initial velocity. The final velocity can be found with a very simple expression, which is the acceleration times the time spent. So the final velocity here is 104.96 meters per second. Over here is the kinematic equation that we will use to solve this problem. Distance equals the initial plus the final velocity over 2 times the time spent. So to solve this problem, if the distance equals the initial velocity, which is 0, plus 104.96, which is the final velocity, over 2 times 32.8, which comes out to roughly 1,721 meters. Now, if we wanted to solve this problem for any other variable, we could use the same set of equations to solve that, which will be seen in the second problem shown here. A car starts from rest and accelerates uniformly over a time of 5.21 seconds for a distance of 110 meters. Determine the acceleration of the car. So again, we start with listing what we know and what we don't. We do not know the acceleration of the car. We do know the time spent. We know the initial velocity. We know the distance, and we don't know the final velocity. So when there are equations with multiple things that we don't know, what we have to do is use multiple kinematic equations. To start out, we'll use the simplest one, which is the same one we used in the previous problem. So what we do here is distance, which is equal to 110, equals VI plus VF over 2 times t. Because we know VI is 0, 110 is equal to VF, the final velocity, over 2 times time. So 220 is equal to the final velocity times time. And another way of putting this would be that 220 over time equals the final velocity. Because we knew from the very beginning what the time spent was, we can say the final velocity was 220 over 5.21. We're going to leave the final velocity in this form and now use the next kinematic equation to solve for what we're actually solving for, which is the acceleration. The final velocity squared equals the initial velocity plus 2AD. Because we know the final velocity, we can just substitute it into here and square the numerator and denominator and it equals 2 times the acceleration times the distance, which we know equals 110. Therefore, because 2 times 110 is just 220, we can divide that from the left side of the equation and get 220 over 5.21 squared equals the acceleration, which is 8.1 meters per second squared. Now, what to know from this question is that seeing that because there were multiple variables that we did not know, we had to use multiple kinematic equations to solve it. And by doing so, we were able to find the final velocity and the acceleration of the car. For the next practice problem, Upton Chuck is riding the giant drop at Great America. If Upton free falls for 2.6 seconds, what will be his final velocity and how far will he fall? All right, before we do this question, we need to know something very important about questions where we see the phrase free fall. When an object is in free fall, we know by definition that the acceleration of the object is just going to be gravity, and the initial velocity is always 0 unless explicitly stated that the object was thrown. Knowing that, we can go into the question. Now, what we know is the initial velocity, which is 0 meters per second, the acceleration, which is equal to g, which is equal to negative or positive 9.8 meters per second squared. We also know the time. The final velocity, we can do the same thing as we did in problems 1 and 2 and multiply the initial velocity times time, which is going to be equal to 25.48 meters per second. Or the final velocity, yeah, exactly. So now we have to solve for the distance, which is vi plus vf over 2 times t. The distance here is unknown, so we substitute it into this expression. We get 25.48 plus 0 over 2 times 2.6, which is equal to 33.1 meters, which is the distance. And we also know the final velocity. Next practice problem. A race car accelerates uniformly from 18.5 meters per second to 46.1 meters per second in 2.47 seconds. Determine the acceleration of the car and the distance traveled. So here we don't know two variables. We don't know the acceleration and we don't know the distance. What we do know is the initial and final velocity and the time. So a very simple equation for acceleration is delta v over t, which means the change in velocity over time. So the change in velocity is going to be vf minus vi, so 46.1 minus 18.5, over the time in seconds, which is 2.47. So we get the acceleration equals 11.2 meters per second squared. Now, what we can do here is, since now that we solve for acceleration, we solve for distance. So it's vi plus vf over 2 times time. So it's 18.5 plus 46.1 over 2 times 2.47, which is equal to 79.8 meters. So just by using these two simple kinematic equations, we got the acceleration and the distance traveled by the car. For the last practice problem, a feather is dropped on the moon from a height of 1.4 meters. The acceleration of gravity on the moon is 1.67 meters per second squared. Determine the time for the feather to fall on the surface of the moon. This question is another question regarding free fall, and so we will use g. However, because we're on the moon and gravity is stated to be a different number, we will use that value of g instead of 9.8. So we know the distance traveled, we know the initial velocity, and we know the acceleration. The equation we're going to use here is going to be distance equals vi times t plus 1/2 a times t squared. So the distance 1.4 equals 0 times t, which is 0, plus 1.67 over 2 t squared. And 1.67 is the acceleration over 2. So what do we get here is 2.8, because we multiply the 2 over to this side, equals 1.67 t squared. T squared equals 2.8 divided by 1.67, and t therefore equals 1.29 seconds. And this is how long it takes for the feather to fall into the surface. So all the questions, the 5 questions done in this video, were taken from the physics classroom, so full credit to them. Here's some additional resources you can use to practice. The first 2 links are practice questions from the physics classroom, and then a basic overview of the 4 kinematic equations. After this is a very good resource called physexams.com, and this is several practice questions more advanced about the kinematic equations. And then the last one is an 88-page PDF, also about the kinematic equations for study. So I hope this video helped explain the kinematic equations and how to use them in a little bit better detail to you guys. And I hope you guys have a great day. Please remember to like, share, and subscribe to my channel. And I'll see you next time. Bye.